Look closely at the streetscape of any ancient metropolis. The density is staggering, a vertical crush of commerce and life packed into limited space.
But before the mechanical lift became commonplace, height was not merely an architectural choice. It was a profound physical constraint. Human muscle power dictated the limits of construction.
Buildings were fundamentally defined by load-bearing walls, solid masses designed to resist gravity, pushing down from above. This meant that stacking complex functions, like offices, residences, and markets, required immense, slow, and localized labor.
The resulting urban fabric was horizontal in its ambition. It spread out, constrained by the sheer weight of its own materials.
The city lived at street level, a magnificent sprawl limited by what men could physically lift, carry, and stack without collapsing under their own collective weight.
The limitations of horizontal expansion necessitated a radical rethink. How do you build up?
The early solutions were rudimentary, often involving simple winches or inclined planes mechanisms designed primarily for hoisting goods rather than moving people efficiently.
Transitioning from brute force lifting to reliable vertical transport presented an immense engineering hurdle. Early lifts struggled with speed, safety, and consistent reliability.
These weren't merely matters of mechanics. They demanded a complete rethinking of structural integrity and human interaction with machinery.
The gradual adoption of dedicated passenger elevators signaled more than just convenience. It represented the industrial mastery over gravity itself.
It was the first true vertical axis in modern urban planning, fundamentally changing what architects dared to conceive and build at height.
Pioneers like Elisha Otis addressed these fears with safety brakes, transforming a dangerous novelty into a dependable utility. This breakthrough in
Before this reliable mechanical lift, the function of tall buildings was inherently limited. Structures were primarily conceived as residential blocks or ground-level retail anchors.
The ability to move people and goods vertically with predictable ease fundamentally redefined architectural possibility. Suddenly, an entire floor could be dedicated not just to living space, but to specialized commercial functions, the modern office.
This created a new economic value proposition, the vertical division of labor. Buildings became complex machines for commerce, where every story held distinct, marketable utility.
Height itself became synonymous with prestige and accessibility, transforming city skylines from simple groupings of structures into layered, highly efficient economies. This new vertical stratification fueled unprecedented urban density. Corporations began staking claims on prime high-rise real estate, creating distinct economic zones that dictated everything from commuter patterns to global market power.
The corporation quickly realized that height was not merely about maximizing square footage. It became a potent visual metaphor for success itself. The skyscraper did more than house commerce. It codified social status.
A building's verticality began to translate into a rigid, visible class structure. Those occupying the coveted upper floors enjoyed panoramic views and filtered light, literally looking down upon the street-level activity below.
Conversely, ground floor retail remained accessible but often relegated to transactional anonymity. Architectural design rapidly absorbed this economic stratification.
The sheer scale of curtain walls and monolithic lobbies became statements of capital, declaring a corporation's power before anyone even entered.
To build high was to declare market dominance. It was the ultimate physical manifestation of wealth and influence in the modern American metropolis. This hierarchy wasn't accidental. It was engineered into the very blueprints.
From grand lobbies.
But the sheer verticality of these towers tells only part of the story. The elevator is not a standalone object. It is merely the most visible symptom of an immense hidden infrastructure.
To support modern life at this scale, to power thousands of people day after day, requires a complex web of unseen systems running alongside the lift shaft.
These include massive electrical conduits, hatchback ducts for ventilation and climate control, plumbing lines, and communication trunk cables. This vertical infrastructure is its own industrial ecosystem.
It demands dedicated mechanical shafts, sophisticated power grids, and constant maintenance.
The elevator car itself is just the passenger interface. The true marvel lies in the supporting architecture, the silent circulatory system that makes the entire edifice function.
These interwoven systems, from high-voltage feeders to fiber optic spines, are what truly define vertical urban density. They transform mere buildings into self-sustaining complex machines, enabling modern life's relentless upward expansion.
The 20th century witnessed an exponential leap in elevator capability. Early pneumatic and hydraulic systems provided incremental improvements, but the true revolution came with electrification and advanced control mechanisms.
Suddenly, speed was no longer a limitation. It became an asset. Engineers mastered the physics of vertical travel, enabling buildings to reach unprecedented heights.
The ability to move large numbers of people quickly across vast vertical distances fundamentally redefined urban scale.
Cities like Chicago and New York did not just grow taller. They grew denser, creating the massive concentrated cores we recognize today.
This mastery of verticality was perhaps the single most crucial enabler of modern global city life. From steel skeletons to curtain walls, these vertical arteries became essential infrastructure.
They supported everything from corporate headquarters to residential towers, solidifying the skyscraper as the defining architectural symbol of global economic power.
The evolution did not stop at mere mechanical efficiency. Today's elevators are complex computational devices, seamlessly integrated into a network of smart building management systems.
Modern control algorithms don't just move people, they predict movement. They analyze real-time occupancy data and traffic patterns to optimize flow, minimizing wait times and preventing the bottlenecks that plague massive modern towers.
This level of digital intelligence allows buildings to operate with unprecedented efficiency. Furthermore, advanced sensors facilitate predictive maintenance, monitoring components before failure occurs.
These smart systems ensure reliability while maximizing throughput, proving that the elevator's role has shifted from a simple transport mechanism to an integral component of the building's operational nervous system.
Consider high-rise structures like the Burj Khalifa. Their sheer scale demands this level of precision.
By anticipating demand and managing vertical traffic dynamically, these smart lifts ensure that the modern skyscraper remains a fluid, functional ecosystem.
But the story of verticality is not finished with steel and glass. The next frontier lies beneath our feet and above our heads, driven by technologies still in advanced research.
We are looking at systems that promise to bypass the limitations of traditional cables and rails entirely.
Imagine magnetic levitation trains gliding silently through city canyons, or high-speed funiculars connecting distant peaks without visible support structures.
Even more radical is the concept of integrated subterranean networks, multi-layered transit arteries that move people and goods far below ground level.
These aren't mere sci-fi concepts. They're areas of intense engineering focus, promising to redefine urban density and connectivity in ways we can only begin to predict.
The future of movement will demand an even more seamless integration of transport into the very fabric of the city itself.
To understand this trajectory, from elevated transit lines to subterranean arteries, we must reassess what defines a modern city.
It is easy to view skyscrapers as mere architectural triumphs, but that perspective misses the essential mechanism: vertical mobility. The elevator did not just provide convenience. It fundamentally altered the physics of human settlement.
By conquering gravity's constraints on an unprecedented scale, it allowed populations to achieve densities and economic organizations previously unimaginable. Suddenly, land value was decoupled from ground-level accessibility.
This shift meant that the city is not simply a collection of buildings, but rather a complex, multi-layered piece of civil engineering infrastructure.
The elevator is therefore not just an amenity. It is a foundational pillar upon which modern urban life rests. This vertical integration enabled specialized zoning and unprecedented density, transforming mere structures into functional ecosystems.
The elevator thus became the